SwayamPrabha. Digital India. Educated India.
Good afternoon, everybody. Today we'll try to discuss that remaining part of the microjoining and nanojoining technologies. So to do that, first of all, we'll try to look into the what are the works done so far in the field of medical devices using different microjoining technologies. So if we see that one of the important aspects for the medical devices that actually made from the wide range of materials, but difficulty in that sense that when we try to join two different metals, similar kind of materials or non-metals that generally used in the medical devices. So here first thing is that we need to ensure that to choosing any materials or methods that it should be safe to be implanted in the human body, and it should be biocompatibility and should be extremely reliable for the human body. So we should look into that aspects before processing any materials for medical applications, either in terms of the processing working with the any medical devices or any implantable things that is implanted in the human body. So most of the cases we use that hermetically sealed enclosure, and that material should have or characteristic of the typical the long term corrosion resistance. So these are the typical requirement for the application of the any kind of processing technologies, specifically for the medical devices. So what are the typical materials we use for the medical application, or maybe in the point of view of the microjoining technologies? So that most of the materials we use here, the titanium, safe memory alloy, platinum alloy, stainless steel, and sometimes the plastics. So if we look into all these materials and what are the different welding technologies normally applied for the medical devices, that are the resistance welding, ultrasonic welding, transmission laser welding, and radio frequency or dielectric welding, and most in the form of a spot and the seam welding. These are the individual welding techniques we generally apply for the medical devices, but complexity arises depending upon the geometry of the actual component. Specifically, when we choose any kind of welding processes, must have look into the different aspects. For example, it should be least affected by the surrounding materials when we choose some certain joining technologies or welding technologies for the medical components. That is the most important requirement. So in that case, maybe very precise control of the heat source is required. So in that aspect, probably most commonly or in generally laser welding techniques is more suitable in that respect. So in general, what are the typical challenges and issues in selecting the materials for the microjoining of the medical components and as well as devices? First thing is that the compatibility of the biocompatibility performance as well as the electrical conductivity sometimes requires for the material. Corrosion resistance, surface quality or surface finish should be very high even after welding, and the micro scale weldability of the materials, and most of the cases the weldability of the dissimilar combination of the materials or dissimilar configuration of the materials is actually necessary, and that we face or that actually brings the different challenges in the microjoining application of the microjoining technologies. So to even after all these challenges, so there are several materials and joining methodologies has been so far used, or it is evolving for the specific type of material such as the platinum, tantalum or titanium. For this material normally resistance, laser and ultrasonic welding technologies are used. Of course, these welding technologies are used in the micro scale application. Copper alloy and stainless steel normally resistance, laser and sometimes we use the bridging technology. And solder, for the lead free solder, in that case we use the welding methodology or joining methodology like bridging, soldering and ultrasonic. And plastic materials probably we use the laser and adhesive, and specifically for silicon it is we generally use the different adhesives. So, because adhesives is one kind of joining technology. So, these are the materials and corresponding joining technologies normally used in case of micro joining applications. So, first we focus into that specific micro joining technologies, and for a specific vesicular devices. These are the vesicular devices, actually catheters and guide wires to balloon angioplasty and stents. These are the here in these devices we use the welding technology in different way. So, maybe if you look into that figures, probably in this case guide wire or catheter basically is a kind of wire or a kind of hollow tube. So, that is typically used, and in this case it may be the size and shape may vary according to the applications and having the different functionality of the different component of a complete medical devices or medical component. So, here if you see, the catheter is a thin tube made from the medical grade materials that can be inserted in the body, generally single use device. So, in this case this sometimes when the single use device, sometimes we use in that way that high costly nickel titanium alloy can be used for this in this medical devices. So, sometimes it is necessary to replace some part of the nickel titanium wire or maybe tube replaced by the stainless steel tube. So, that can be the cost effective methodology. So, in that case it is necessary to join the stainless steel tube or wire to the nickel titanium alloy. So, in that way it is applicable for the joining technology for the specific devices. So, if you see that guide wires for the catheter application, some part of the wire may be joining small diameter wire in butt weld configuration. So, mostly joining of the SS316L stainless steel and wire to the nitinol end effector, or the some part of the nitinol is necessary to join. Of course, SS316L is used because it provides the good transmission and low cost, but alignment of the diameter and control in the weld zone is really very difficult. So, in this case probably laser can be or laser welding can be a good solution. Like balloon catheters, joining of the polymer balloon to the polymer tube on the guide wires is sometimes required. So, in this case either direct laser welding or adhesive bonding generally used in this case. So, of course, in the generally single use device, this vesicular device where we use the catheters and the guide wires or joining the balloons, in this case it is generally single use device, but if you look at the stent, is the permanent implant is required. In this case typically the stent are produced from the laser cut and from a tube and welded on a small wire. So, objective is to this stent is the actually need to put is the collapsed and delivered in the very precise location, that is the objective. So, in this case challenges of the excellent surface finish and the edge finish, control of the heat affected zone and extreme control on the orientation and the laser cutting path is the main issues, specifically the application of the laser in this medical components. Sometimes we use the pumps and sensor also. So there are several types of internal and external pumps are used. For example, the insulin pump and left ventricular assist device. So in this case, we use it is necessary the joining of the pumps and different type of sensor, electrical circuit board is necessary. So what are the challenges? If we see that welding and joining of the plastic foil is necessary in this case, bonding sometimes fragile semiconductor with respect to each other, or sometimes microscopic circuit assembly is required, the wire or tube attachment for the interconnection is also required. So all this joining or different types of materials, they are having huge variety of the properties is specifically necessary in these cases. Then we find out the micro joining of the medical components, that pacemaker manufacturing. It's a pacemaker is basically mainly a pulse generator and leads. So pulse generator consists of the one is the battery and the second is the circuit board. So battery basically to generate the electricity and circuit board to generate control and deliver the pulses. So that is the main purpose of pacemaker manufacturing process. So in this case, battery is hermetically sealed, laser sealed to prevent any leakage of the chemicals. So it is sealed in such a way that there must not be any leakage to the chemicals during the body. Second part is that battery and the circuit board are inside a titanium case that is also hermetically laser sealed. So when during the sealing, probably we need to put the laser source, and then we seal the materials or these components, and then we use a complete making a package of the complete pacemaker. So of course in this pacemaker, the internal circuits is generally connected through the brazing process, but connector block sometimes encapsulated in a biocompatible polymer such as polyurethane. So here, which is interconnected by the titanium wire, and that the typical welding process here is using either laser and resistance micro welding processes. So we can see even for pacemaker manufacturing, although there are several components we can use it, but it is also necessary all this precaution. For example, should not be leakage, any chemical components exist in the battery, and then that to do that, it is always we need the hermetically sealed sample, and that we using laser, and most of the cases we use the circuit board, maybe is the soldering, and maybe internal circuit either soldering or brazing. We can, it is connected, that is also one kind of joining technologies. And finally it is necessary that titanium, titanium is a very good biocompatibility material. So sometimes it is the certain part is encapsulated within the titanium case. So several in this all these components we find out that there is a tremendous application of the different welding and joining technologies in case of pacemaker manufacturing. Maybe see the other radioactive seed implant, that is also one kind of radiation therapy that has been developed as an alternative to the external beam irradiation for cancer treatment basically. So in this case we use a radioactive substances sealed in a seed, and that is necessary to implant it near the cancer. So in this case the cancer cell is destroyed in this way, the cancer cell is destroyed by the energy given off the radioactive material. But the issues are the sealing of the radioactive substances, that is also that is generally done the titanium case and using the laser microwelding process. And finally the laser microwelding processes, that is the only application of the microwelding in this case. But difficulties is that although we can use the laser microwelding process, so we need to control the heat affected zone to the radioactive material. So that's why it is necessary to develop and suitable process methodology using the laser microwelding process for this kind of very precision manufacturing. So apart from the, of course, when you use the different micro joining technologies, for the medical devices is it is necessary to mechanically test the different welded joints. So, of course, in conventional welding processes we use the different type of testing, tensile testing, compressive testing, or maybe sometimes bend testing. All this kind of testing we generally done in the conventional welding processes, but specifically all this type of micro joint components. So, small scale tensile testing equipment is required to do the any kind of tensile testing. For example, we see some examples are also here. Here we see that butt joint. So, joining of the two components, if you see two metals are joined, is butt joint configuration, and in this case the tensile load is acting in the outward direction, and we try to analyze the load versus the we can failure mode or joint strength using this simple application of the tensile load. But this, since sample size are very small, so we need to consider all these tests in the micro tensile testing, in the micro tensile testing equipment. So, from here, from the tensile analysis we can find out the joint strength or maybe the failure mode. Similarly, lap joint configuration, that it is necessary to test the weld joint. If the joint is lap joint configuration, then some sort of shear load, we can find out the shear strength of this joint. So, in the second one, but this is the lap joint, and sometimes we find out the peel test. So, application of the load here, and here is the welded joint, and there if you do the peel test we can find out the strength of the joint with this geometry configuration. Of course, with the lap joint way, the actual joint is the lap joint. Finally, also it is possible to do some torque test also. If the lap joint configuration, here we can apply the torque to find out the joint strength, and we can do the failure analysis. So, this like conventional welding processes, even for micro welding application, these are the typical type in the butt joint configuration or the lap joint configuration of the weld joint are subjected to different kind of tensile load, shear load, peel test, or maybe application of the torque can deduce some kind of mechanical properties or failure analysis typically used for the medical devices. Now, after doing the analysis of the medical components, we can look into that what are the advancement is actually happens in the specifically laser micro welding processes. So, to analyze this thing, there are several advancement happens till date in the micro welding or micro welding technologies, specifically using laser in a different way. So, we will try to look into that. So, here application of the laser, control of the laser source, probably useful to design the different type of, or to develop the different type of micro welding technologies. So, first we will look into that. One of the such technique is the shadow technique. So, shadow technique stands for the stepless, high speed, accurate and discrete one pulse welding. If we look into that, shadow comes from this first letter of this word, and that is highlighted in the lead color. So, based on that, that is called the shadow technique. So, what actually we understand from this shadow technique? If you see that in principle the transforms macro laser spot weld to the micro laser seam weld, that is the basic principle. So, here maximum pulse length is possible in the diode pump laser. That is why diode pump laser is typically used to develop these shadow techniques. So, little bit explanation of these shadow techniques if we look into these two figures. So, if we look into the first figure, if we see that the fusion zone, it looks like that after application of the laser, obviously it is a pulse laser. So, fusion zone kind of overlapping with respect to the speed, or we can say that it is a accumulation of the several spot that simply overlaps. Now, pulse mode, and the power is 300 watt in this case, and pulse, I think pulse energy is 27 joule, and the pulse on time 5 millisecond, and the pulse frequency or pulse repetition rate is around 25 hertz, and velocity is basically 300 millimeter per minute. So that means it's a very high velocity, 300 millimeter per minute, I think 5 millimeter per second, not very high, at a moderate velocity we can say. So with this pulse characteristics, that means with the typical pulse parameters, some pulse on time, frequency, and the power and the pulse energy, it is and with this specific speed means what way we are moving the laser source. So with this configuration we can find out there is the overlapping of the several spot. But if it is possible, since there is a pulse duration is 5 millisecond, now if it is possible to move that entire duration or entire length throughout the duration of the pulse, so through it's a, maybe I can say that it's a kind of equivalent way, like a continuous mode of laser welding process. So in the continuous mode of, there is a continuous application of the power, or maybe continuous application of the power, so that it can make a very smooth surface appearance, not like pulse in the overlapping. But the similar kind of things in case of pulse laser welding, if it is possible to cover the entire length of the weld in single over the duration of the pulse on time, then probably that can be converted as a very single pulse welding process. So if the second figure, if you see here, using the shadow technique is nothing but the moving of the pulse energy is 9 joule and pulse shape, and it's a pulse duration is 20 millisecond and velocity Vf equal to 30 meter per minute. So it's a very high velocity. If when the laser is moved with a very high velocity, probably the weld length can be covered within the duration of the pulse. So that is the implementation. So instead of using the several pulse overlapping, we can use only the single pulse, and we can use it equivalently in the form of as a continuous laser. So that is the technology generally we use in the shadow process. So that is the one kind of development, but of course in this case the several trials are required, and that may be the material specific to find out the actual parameters that can be applicable using the shadow technique. So this is one type of advances in the laser microwelding process. Now if we look into the other welding processes, that is called laser droplet welding. Of course, the purpose of using the or development of this process, typical microwelding process, is to that overcome the gap bridging. So gap between the two plates or gap between the two different samples, specifically very high reflective materials and very high heat sensitive materials. So on these typical types of materials, using the conventional laser welding processes, sometimes it becomes very difficult. So to do that, alternative method, probably it is possible some using the liquid metal droplet that is created at the end of a wire, and of course using some pulse laser. So in this laser droplet welding process, there is a that consists of the pulse laser with the triple optical beam splitting. So the beam splitting, the triple optical beam splitting system, that is the one requirement, and normally NDOAG laser can be used, or probably this process is developed using the NDOAG laser, and a wire feed system. So feeding of the wire, because it is necessary to produce the molten droplet. So that comes from the wire. A target positioning system. So a target positioning system, when you targeting the droplet of the metal on a specific zone, because it is a microwelding process, it's very precisely we have to fix the target position. Shielding gas supply, simply protect the molten pool from the outside atmosphere, and the mechanical positioning system. So these are the typical components of the laser droplet welding, but how it works. So if you look into that, specific in general, this thing is the if you see that this phases of the process is that first is the in terms of the droplet creation, second is the droplet detachment, then droplet flight and droplet landing to the accurate position, and then finally droplet solidify, and then after solidification, droplet solidification, the two materials can be joined. Even there is a huge gap between these two materials. So, how it works? If we look into that typical pulse shape in the this figure shows the power versus time. So, initially the duration of the pulse is more and the moderate having the pulse power is good, moderate pulse power. So, that actually helps to create the droplet by melting the wire in this case. And then next is that the magnitude of the power is very less, and over certain distance within that it is actually the droplet is moved along with the wire towards the target point of the welded joint. And third, it is possible to use that high power but over a short duration, high pulse power but over a short duration. So, that actually helps to droplet detachment from the wire, and it actually exactly put into the exact position of the weld joint. So, that actually helps to create the weld joint in this case. So, typical application if we see that stainless steel, similar kind of material joining, titanium and stainless steel, which is really very difficult to join in the conventional welding processes. Most of the cases the joining of titanium and steel is in good joint can be obtained using the solid state welding processes, but using the laser droplet welding process the titanium and stainless steel can be possible to join of 200 micrometer thick plate, and even this weld joint is also possible if there is a gap of the 200 micrometer in this case. So, in this perspective of the size of the plate thickness, the gap of 200 micrometers is really very big in this case. So, of course, using this technology that kind of problem, typical problem can be solved. So, apart from this laser droplet welding, other advanced welding technologies like laser spike welding, that is also developed, and this is also developed on the keeping in the this thing the normally in the BART joint configuration. So, sorry, lap joint configuration. Here in the gaps, if there is a gaps in the micro welding exist, that is always problematic, and sometimes it also exists by if we look into the overall structure of the any kind of devices. So, when you try to do any practical application of the devices, sometimes the gap may be very big. So, in this case the one of the suitable welding technologies is the laser spike welding. So, that this welding technology is useful even there is a huge gap. What are the principle in this case? The recoil pressure driven material flow to bridge the gaps in lap joint by spot welding technology. So, lap joint configuration and normally use, and specifically the spot welding technology we use, but it creates some recoil pressure driven material flow. Let us see how it works. If you look into the process itself, first melting using the low power in the upper layer. So, upper layer is melted using the low power laser, and then when using the low power laser probably it remains in the conduction mode, not the keyhole mode. So, we should use the conduction mode laser for the melting of the upper layer. Then it is necessary to allow sufficiently large or completely penetrated weld. So, we need to increase the power such that it completely penetrate the weld. Then again increase the laser power to generate sufficient recoil pressure. So, that sufficient recoil pressure that actually creates the diaphragm like liquid pool that actually contact with the lower layer. So, even there is a huge gap in the upper and lower layer, that diaphragm like liquid pool actually with contact with the lower layer. Now, the joint can be formed, it looks like the superficial surface melting or like a bridge like adhesive between the two plates. So, So, this is the one, this is the laser spike welding process, but if the lower surface is very clean, so batch like addition is possible in this type of typical joint, and if lower ledge is too conductive, then it is very difficult to join, because with the application of the heat, apart from the creating the or melt increasing the large volume of the oil pool, that the heat will be conducted away. So, application found out for this typical welding process, the stainless steel of 200 micrometer thick material. Another advances in laser microwelding technology, if you see, that is called twist technology, that is transmission welding by an incremental scanning technique. So, in this case, that high beam quality laser like fiber laser, it is a basically easy degradation of the thermoplastic material is difficult to apply in case of thermoplastic material, and when the laser can be moved at very low velocity. Fast rotating and the slow linear motion of focused high quality laser beam can be used in the different way, so that local and temporal laser beam modulation strategy can be used in this case. Second thing is that if periodic beam deflection dynamically is also applied to control, that can control the fusion and the application. So, that means not exactly focusing on the laser beam for a long time in a particular zone, rather if laser beam we control if we periodically deflect the laser beam, and of course, if we control the laser path also, that is better opportunity to create damage of the any kind of thermoplastic materials. So, in that case, it is possible to avoid any kind of voids or porosity can be reduced. So, if you look into these figures, so different scanning path can be followed. It can be circular, it can be linear, but linear in the zigzag way, or some other combination of the laser path, and that comes from the periodic deflection of the beam. So, basically by locally and with the time scale, if laser beam modulation strategy can be adopted, so that high power laser beam can be used easily in this case. So, that not only reduce the damaging of the thermoplastic materials, but at the same time it try to reduce the other porosity and the voids, that's kind of defects in this welding process. Otherwise it may exist if you try to use the laser in a conventional way. So, that is why twist technology is mainly used for transparent polymers. Even transparent polymers, if you want to join using the twist technology, there may not be requirement any absorbing additives. Otherwise, conventional welding process, if you do not adopt the twist technology, when you try to join the two transparent material for the laser wavelength, so in that case some absorbing medium is required in interface, but in this case that is not required. That is the main advantage of this twist technology. Now, apart from the advances in the different micro joining or micro welding technologies, there is some advancement also happens, or till some research work is going on in the development of the different nano joining technologies, and most of the cases these are confined in a research and development section, but not commercially applied, but we will try to look into the few nano joining technologies. So, if you look this here, if you see what are the different type of nano joining technologies. So, here if we see that the solid state welding nano joining technologies that we use, that is called electron beam welding, diffusion bonding, ultrasonic welding, and the cold welding. These are the all solid state welding process, and that is used in nano joining technologies. Liquid phase reflow, soldering, resistance soldering, active brazing, laser brazing, these are the typical processes in the category of brazing and soldering, typically in case of nano joining technologies. Laser beam welding and resistance welding, these are the two fusion welding technologies we observed in the application of the nano joining technologies, and finally the adhesive bonding are also used for the nano joining technologies. So, we will look into the few nano joining technologies. here. So, first is that looking at the solid state nano bonding. Here the principle is the diffusion nano bonding using metallic nanoparticles. We have already discussed that when we try to use the nanoparticles, the surface area and volume ratio basically is very high. So, that is having the different properties that may not exist is the other is the very finite size of the particles or maybe a larger size of the particles. So, nanoparticles is normally sintered to form the networks, and these networks are joined to the substrates by diffusion, and the main driving force for the diffusion is the to reduce the surface area. Now, with reduction in the size of the nanoparticles, the diffusion is actually enhanced. So, diffusion mechanism is enhanced for the further reducing in the size of the particles, because in this case lower activation energy is required and there is an increment of the specific surface energy that actually results in the decreasing of the sintering and bonding temperature. So, if the size of the nanoparticles is even it is reduced, then it actually enhance the diffusion bonding mechanism, and at the same time during the when you try to make the joining by the sintering process. So, in this case there is a decreasing of the sintering temperature and the bonding temperature can be reduced if you try to reduce the nanoparticle size. So, that is the in that principle the nano bonding of the different particles can be possible. But this is the significant in the development of the low temperature joining process for polymeric based microelectronics applications. So, it is best suited for the microelectronics applications and specifically polymeric base, and that is why it is necessary to when you try to application this technology for the microelectronics application or for the polymeric based materials. So, in this case it is necessary to conduct this process over the low temperature. So, that is only possible in the because nanoparticle size is very small. So, in that actually it enhances the reduction of the temperature of the process, overall process, and of course sintering temperature. So, that is the one of the nano bonding technologies is till it is going on in the R&D phase. Now, we look into that solid state nano bonding. So, here if we see the direct joining of the carbon nanotubes using a fused electron beam. So, if we see into the figure, there are two carbon nanotubes and it is necessary to join between the two carbon nanotubes, but of course, we need some external energy. So, here fused electron beam can be used to joining these two carbon nanotubes. So, figure A shows that a single wall carbon nanotube of 2 nanometer in diameter crossing with another single wall carbon nanotube which is having 0.9 nanometer in diameter. Now, 60 seconds of electron irradiation promotes a molecular connections between the two tubes that actually forming a junction. So, of course, in this case it is necessary to very precisely control the electron beam, and that should be focused on the exactly on the joining of the two nanotube. So, here the electron beam is actually directed to induce the structural defect like vacancies or interstitials of the crossing point of the carbon nanotube. So, at that point when you create the vacancies or the interstitial, in that point it is necessary to control the electron, and then self arrangement of the carbon after creating that kind of defects. Basically, the vacancies or interstitial, that is the one kind of crystal defects. So, if we using the electron beam, if we try to create the defects at the joining point, so then after that self arrangement of carbon atoms can occur and at the high specimen temperature, and they can bond together, that means two different carbon nanotube. So, this is the one type of technology nanotube, but still it is under in the R&D section, research and development section. Another point is that nano soldering and nano brazing. So, even like conventional and micro scale soldering and brazing, even for nano soldering and nano brazing, probably we understand the soldering and brazing. The second material we try to put very precisely that second material join the other two material. So, for the successful nano soldering and nano brazing, a tiny amount of the solder has to be very precisely delivered exactly at the bond area. So, this is significant in the assembly and the integration of the nano electronics industry, it is very important. So, this type of joining technologies, or maybe say nano soldering and nano brazing technologies. So, how it can be happen that nanosecond pulse laser is used to melt the gold nanoparticles, and that gold nanoparticles actually try to join the platinum nanoparticles. So, first figure is this one, electron micrograph of the platinum and aluminum gold networks formed by the laser brazing, and the second one is the platinum nanoparticles are held together by the molten gold particle. So, here if we see that very precisely, if it is possible to put the gold particle in between this platinum particle, that can be joined with the application of the even nanosecond pulse laser. Of course, there is a scope of using the femtosecond, we can more precisely control the source of the heat. So, in this case, that is also possible to precisely use the femtosecond lasers also to create that kind of nano joining or nano soldering or nano brazing technologies. Now, we come to that fusion nano welding. So, fusion nano welding, what are the typical heat source is used? So, in this case, that laser beam joule heating, that means joule heating means we can use the resistant welding technology, and welding of the platinum nanowires to that is also one type of fusion nano welding. The two nanowires are touched end to end by piezoelectric manipulation and followed by a welding current. See that first figure. So, here if we see that welding of the platinum nanowire, if the first figure if we see the resistance nano welding. So, platinum nanowire to the very thin gold wire. So, if it is possible at the joint interface there is some resistance, and if it is possible to pass through the current, and if we create some heat at the interface due to the resistance between these two materials. So, that is probably sufficient to produce the fusion nano welding process between these two materials. If you see the right hand side figure, here this figure we see that two platinum wire nanowire before current supply and before current supply, but if we put it using handling of the proper position of the nanowire, but handling of this kind of nanowire or maybe nanotube is very difficult. In this case, the piezoelectric manipulation is required to exactly put or to at the proper position of the two different nanowire. So, after putting the specific position of this nanowire, then current can be applied, and that can be joined by the resistant welding process. So, third figure, if we look into this figure, here if you see the femtosecond laser nano welding, the gold particles with 100 femtosecond laser pulses. So, femtosecond nano welding means the nanoparticles, if we use the ultra short pulse laser, here it is a femtosecond pulse laser. So, that gold particles can come with each other, and they can be joined in between by the means of the fusion nano welding process. So, if you see that all these cases, although we use the laser beam and the either resistant welding, these are two typical nano welding processes so far developed for the nano joining technologies, but in this case of course the control of the heat source is very much necessary to get the successful. Of course all this methodology or process of the nano welding still in the recent development stage. So, If you look back to the different nano welding, micro welding technologies, and if you see overall analysis of all these processes or technologies developed so far, we see that first thing is that very small possible focused beam in the form of a very small spot or in a even almost like a line of the metals or non-metals are possible probably in using the laser process. So, that is why most of the cases you found out the laser micro welding or nano welding technologies has been developed as compared to the other developed heat sources. High quality defect free joints are possible for highly conductive materials such as gold, silver, copper in jewelry industry, specifically using different micro welding or micro joining technologies. Micro joining technology, of course, it is still continuously developing in some of the new fields like electronics, biomedical instrumentation or the sensor and packaging industry, by taking the advantage of the other specific developments like robotics and the automated system, and of course with the help of the very precisely controlled as a laser source. So, all actually helpful using this, or there is a several development of different micro joining technologies also going on. The successful joint dimension so far from this investigation is find out that specifically I am talking about the micro joining technology, that 10 micrometer with the superior joint quality is achieved, titanium, polyamide and glass, and of course very difficult to weld material such as aluminum alloy are successfully joined by the laser micro welding process. If you see the various soldering processes and alloys widely used in the micro electronics industries, interconnections, and of course in packaging industry that have been modified, and further development of the further process of nano joining is also required in this case. We have also observed that focused electron beam can be widely used in micro and nano joining technologies, specifically joining of the carbon nanotube. So, we found out that focused ion beam, which is also another relatively new energy source, that can also be utilized for the making nano junctions using in different nanowires. So, what are the future development and challenges for in the micro joining and nano joining technologies? That first coming to the mind that exist future challenges in the current scenario of micro joining and nano joining field for the both simulation tool as well as the experimental characterization. So, we can find out that several different types of the dissimilar combination of the materials, maybe characterization of the welding technologies, like characterization of the welded joint is also necessary, and of course the underlining the physical understanding of this process in terms of the different simulation tool are also not developed so far, specifically in micro joining and the nano joining technology. So, that is the one direction that needs to have the scope of the development. And next is that it is also necessary to understand the underlying heat transfer mechanism in extremely short pulse laser, for example in the femtosecond laser source, and the interaction of the laser with the materials. So, that understanding may help to keep the physical phenomena that actually happening during the any micro joining or nano joining technologies. Of course, there is a need for the more modeling and more experimental studies also required for proper identification of the range of the process parameter to avoid the insufficient joint stress or to avoid the any kind of damage of the material. Basically, the successful process parameter domain is necessary to identify through experimental investigation, that is also required in case of micro joining and nano joining technologies. But real challenge in the metal to polymer joining in the biomedical devices is due to the huge difference in their material properties and the nature of the contact surface. So, we need to investigate more on this specific area, specific the metal to polymeric metal to polymer, because that is most of the biomedical and medical and biomedical instrument and devices, implants also we can find out there is a need to combination of the metals and non-metals joining. So, more and more this type of joinings may be helpful to strengthen the micro joining and nano joining field. So, also it needs to investigate from the various aspects. Finally, the geometric precision and the cost of equipment is another future challenge for the mass production by micro joining and nano joining technology. So, in that case we found out that even for micro joining, some micro joining technologies are also developed under the microscope, which cannot be handled in the conventional processes. So, in that case probably that precision is required, precision when we try to develop in the any kind of micro joining or nano joining technologies. So, that is the cost is the real challenge and nowadays. So, now after discussion of these different micro joining and nano joining technologies, so at the end I am trying to discuss some numerical problems that related to the different micro joining technology that may help to understand the process and in some mathematical point of view. So, let us look into the one example for the micro joining and nano joining technologies. First is that if you see in a pulse laser microwelding process, the following parameters are noted: that laser scanning speed 4 millimeter per second, pulse energy 6 joule, pulse width or pulse on time 5 millisecond, pulse frequency 20 hertz, and assume the shape of the pulse is like a square. Now, if you look into this right hand side figure, if we see that this is the typical temporal pulse shape. So, pulse that maybe you can say the x axis represents the time axis, y axis represents the power in this case. So, pulse on time is the duration of the pulse, the on time, and maybe if we see that this is the complete one cycle time. Over the cycle time, some initial time or maybe some time would be that is called the pulse on time, and remaining time is the pulse off time. So, that completes the one cycle time. So, the area over this shape of the rectangular pulse shape, the area covered by this shape, that actually represents the pulse energy. So, pulse energy, that means power into that y axis, since x axis represents time and y axis represents the power. So, that power and duration, the multiplication of this thing, that represents the area, and that area represents the pulse energy. So, looking into this, here we can see we will try to solve this problem. Here, that first thing is what is the peak power and average power in this case. So, if we see that peak power, suppose we assume this is the peak power. So, if we try to solve question number A, so peak power and the peak power and maybe over the duration the pulse on time. So, here the pulse on time is the 5 millisecond, that actually represents the area, that means pulse energy equal to 6 joule. So, from here we can find out peak power equal to 6 joule by 5 millisecond. So, So, from here we can find out that 1.2 kilowatt. So, 1.2 kilowatt is the peak power in this case. Now, if we see what is the average power. So, average power we can find out the average power is that actually estimate over the one cycle. So, if frequency is 20 hertz pulse frequency, so in this case that cycle time 1 by frequency, that means 1 by 20 second. Now, if you see the similar energy balance, the average power into cycle time is equal to the pulse energy, that is the 6. That pulse energy, we assume the over the cycle time, the pulse energy is, although within one cycle, that is the only total amount of the energy, that is the pulse energy. So, that is why from here that you can find out the average power equal to 6 into 20, that means 120 joule per second. So, 120 watt. So, here if you see that pulse, although pulse energy is 6 joule, but from there if we know the shape of the pulse and pulse duration, pulse frequency, all these data are available. In this case, we can find out for this process what is the total maximum power, that is called the peak power. So, peak power is, you can find out 1.2 kilowatt, and average power you can find out that 120 watt. So, that means the in pulse energy, in pulse laser cases, if we consider that is equivalent to the continuous laser, that means there is a continuous application of the energy, then it is equivalent, it is equivalent to the continuous supply of the power. So, in this case laser power is only 120 watt, that means average power is 120 watt, but peak power is in this case is 1.2 kilowatt. So, there is a huge difference, the peak power and the average power. And then next part, what is the pulse uptime? So, definitely pulse uptime, the total cycle time minus pulse on time 5 millisecond, that means 1 by 20 second minus 5 millisecond, 5 into 10 to the power minus 3 seconds. So, if we estimate this thing, we will be able to find out what is the total pulse uptime. So, with this typical characteristics of the pulse parameter, we can find out the different other parameters. So, this is one type of example. If we look into the other example, that correspond to the diffusion bonding process. So, here in the diffusion bonding process, the mass concentration of carbon in present material is 0.2%, and over the time T and a fixed pressure, the mass concentration of carbon increases to 1% and measure at 0.2 millimeter depth of the sample. Assume that the process is carried out at 800 degree centigrade. The activation energy of diffusion is 157 kilojoule per mole, and D0, that is corresponds to the constant, or to find out the diffusion for carbon in iron is 0.7 into 10 to the power minus 4 meter square per second. So, let us look into first the problem itself. So, diffusion bonding process, over the time the carbon atoms becomes diffused and over a certain depth. So, that depth is here 0.2 millimeter, and carbon concentration increases from 0.2% to 1%, and that actually happens over a certain time. That time is T, and but under the condition of a fixed pressure. So, at constant pressure and at all the process is carried out at constant temperature, that means 800 degree centigrade. Now, since diffusion coefficients also is a temperature dependent, so we will try to find out what may be the diffusion coefficients at 800 degree centigrade. So, we use this formula D equal to D0 into e to the power minus q by RT. If we know that q is the activation energy, R is the characteristic gas constant, and T is the temperature. So, basically in this case T, the D0 is given, that constant D0 is 0.7 into 10 to the power minus 4, that is given here, and Q is the activation energy. So, activation energy for diffusion is 157 kilojoule per mole. So, 157 into 10 to the power 3 joule per mole, and we use the characteristic gas constant R equal to 8.314, and this is the temperature, but remember the temperature in this formula should be given in the Kelvin. So, that Kelvin temperature we put it, and we can find out this thing, so that this should be, we should check the dimension of this, that means unit of this equation. So, it should be dimensionless when we put the different units of the different variables in this case. So, then D is coming the 1.6 into 10 to the minus 12 meter square per second. That is the diffusion coefficients in this case for this at this specified pressure and at the specified temperature. Now, concentration gradient is another parameter need to define dC by dx. So, concentration gradient, it is clearly obvious that carbon concentration in that is given kg per meter cube, that mass concentration, that changes from 0.2 to 1%. So, that means 0.2 to the initial and the 1 difference, and it is given in the kg per meter cube, that since it is given in the carbon in the parent metal is this. So, in terms of kg per meter cube, we can find out, we can multiply by the density, and that actually represents that kg per meter cube, 0.2 to 1. Now, what is dx here? Dx is given here the depth. So, it is initially on the top, that carbon present one is the 0.2% on the top of the surface, but the carbon is diffused up to the depth of the 0.2 millimeter. So, 0.220, that is the change of the dx, that is the dx, that means change of the length along x. So, into 10 to the minus 3 meter. So, from here we can find out this is the concentration gradient. Suppose this diffusion happens over the cross sectional area A, and the depth we measure normal to the cross section area in the normal to the cross section area along the direction along the depth amount, that is d. Now, what is volume of the diffusion bonding is basically the cross sectional area, and the normal to the cross sectional area, the depth is d. So, that represents the total volume of the diffusion bonding. So, mass of the diffusion bonding is simply multiplied by the density rho, and of course, this rho we consider the density of carbon. Now, m by A is basically d into rho. Now, T, using this formula we can find out what is the total time of the diffusion, T equal to minus 1 by d, m by A and dC by dx inverse. So, here concentration gradient also given, m by A also estimated. So, d and rho given. So, if we put all these values here, we can find out that T equal to this 31.25 into 10 to the power 3 second. So, that time is required. So, 3.25 into 10 to the power 3 second, that time is required to reach the carbon concentration from 2% to 1% over the depth 0.2 over the depth of I think 0.2 millimeter, and this actually happens that we use the concentration value, and as we assume that this process happens at 800 degree centigrade. So, we use the value of d at 800 degree centigrade. So, this is one type of problem. Now, we look into another type of problem. In a laser welding process, the average laser power is used as 100 watt, and it is focused on circular area of diameter 200 micrometer. Now, what is the laser power density in this case? So, how you can estimate the power density? So, first the diameter which is focused on the sample, that is given 200 micrometer, that means 2 into 10 to the power minus 4 meter, and laser power is 100 watt, and but what is the cross sectional area over which the power is focusing? That cross sectional area equal to A into pi by 4 into d square. So, we can find out the cross sectional area. So, basically laser power density can be measured by P by A. So, power divided by the cross sectional area, and we can find out that 31.83 into 10 to the power 8 watt per meter square. So, that is the power density. So, we can estimate the power density because sometimes this power density is useful to decide whether the laser focusing on any sample, it will create any kind of its conduction mode, or whether it will create some keyhole formation within the sample itself based on this power density. Another type of problem, if you see that in a resistance microwelding process, the applied voltage is 2 volt, and the overall contact resistance between the butt joint sheet is given 2 into 10 to the minus 4 ohm centimeter square. Now, what is the amount of the heat generated? per unit area during this process we need to estimate. We use that heat amount of generated H equal to I square RT. I is the current flowing through the sample, R is the contact resistance, overall resistance, and T is the duration of the time over which we put the current flowing through the sample. Now, voltage equal to I into R. So, from here we can convert H equal to in terms of volt, because current is not given here, only the voltage is given. So, H can be in terms of volt and H by T can be represented V square by R. Now, H by T, V is given 2 volt and R is also given. So, from here we can find out H by T equal to 2 into 10 to the power 4 watt per centimeter square. So, that actually amount of the heat generated per unit area. Now, I think there are some idea about the different welding or micro joining and micro welding technologies, their limitation, their development in the current scenario, what are the development happens for the micro joining and nano joining technologies, their typical applications, and to some extent some kind of numerical problems that will try to help to more mathematically understanding the process, and of course to estimate the different kind of parameters which actually use in the different laser or any other welding processes. Thank you very much for your kind attention.